You guys can hear me, right? Online.
Yes, Prof.
So we got one person in class today. I would zoom the camera around, but I might mess it up. So one dedicated student. Right. Anyway, so there's this homework's a little bit challenging, I guess. So there's two homeworks. So I said, like, you only have to do one if you're a grad student. Undergrads don't need to do any. Right. So, and basically you need to do the first one. And the second one's like a qualifier question. The second one actually you might find kind of easy or not, but basically it should find the second one pretty easy. I don't think you even need to read the paper to like, anyway, so I'll spend some time. And the first one has two parts. It's got one part on dielectric, which is it's a nature paper. And then there's also this, it's basically this nature paper. And then the second part is this from a book, something data-driven, blah, 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 that was published 2021. It's a collection of papers, and then one of the papers has to do with high density. It's a tire company, and I think they're looking at tire compounds. Oh, and there's also, hey, all right, good, two people in here. Nice. We just doubled the student population. It's a miracle. All right, so anyway, it's really hard to find in here, but if you zip down and find HW, then that's 14. Then all the papers are like right after that. There's a couple other machine learning things in here, like there's a Nature paper on synchrotron, like in other words, how you apply it to rapid measurements where you're doing X-ray scattering or some other kinds of things. And then how you reduce like masses of data using machine learning. I think you probably, that's one whole area of machine learning. Anyway, so there's a paper here, it's not on the homework. And then what else is here? Homework. And there's something on melting point deep eutectic. I don't remember what that is. High throughput data driven. So it's just like, it's measurements. It's a lot of measurements. I don't remember what this one is. Anyway, there's a couple examples of totally different subjects, And then the ultra high molecular weight, page 831. This is a book on kind of a recent book, I guess. This. So page 830. It's all machine learning. No, it's all stuff about, I feel what it's about, simulations. And there's one article on machine learning. 831. It's high density, ultra high molecular weight polyethylene. 831. This is so ultra high molecular weight polyethylene is what they use. It's got a really low friction coefficient, and it makes small when it abrades. Anyway, it's used for any place where you want to have low friction, like when you put a hip replacement in the cup, and the ball part is titanium and the cup is this material, ultra high molecular weight polyethylene. Truck bed liners, where you're going to shovel dirt in and pour it out. They're all made from ultra high molecular weight. Coal chutes, like where they take the barge and they pour it onto the thing and it goes down a trough. Those are made out of ultra high molecular weight polyethylene. So it's like super abrasion resistant, and no one knows exactly why. Right. So, and it also, because it's got a molecular weight like over a couple 10, like 5-10 million molecular weight. So you can't extrude it. It's not possible to extrude it. It's the only way to make these things is by, they showed at Lyondell, if you're on that tour, they do drum casting. So they pour the powder into a drum, it melts, but it doesn't flow. So they rotate the drum and then it coats the outside, and then you make like a swimming pool or whatever you want, or climbing toy or whatever from that. And you can make a truck bed liner cold
So then
sheet.
the one for the kneecap, the stay permanent or
Yeah, that's permanent. That's the solution. Because if they put titanium on titanium, it abrades and you get metal shards. And those metal shards, the body reacts to it and builds up a cluster around it or something, like a pus and whatever that is, you know. So it makes a little particles become larger and larger. And then eventually that's the failure mechanism. There's hip implants. So this stuff doesn't make any particles. So it's softer than the titanium, so it doesn't wear the titanium. So it's like a lubricant for the titanium, and it also doesn't make any particles. So it's perfect for that. And they talk about hip implants here. Basically, that's a small use, that's a value added. And those things like, 20 grand for one of the pieces, right? So, and it's just a little bit of the stuff. The main use is going to be like coal sheets and truck bed liners. In any place where you don't have low coefficient of friction. So this is kind of interesting to use. So they have all this input, like what they're going to put in data for the material. And then they're going to say like coefficient of friction and then the wear. So they correlate things and they use neural network to do that. So in that sense, it's pretty well applied, like a simple thing. So I don't want to dwell on that because that's not on the homework, so it's in that book. See, I think it's worth looking at that. And then this is just the garbage pictures. And that's it. Some of the stuff that I talked about in lecture, like the examples I had in lecture, right? So anyway, so this homework, again, like the second part, I don't think the second part you even need to read the paper. You can just answer these questions. But you can look at the paper if you want. But basically, it's how do you interpret a DSC curve. And then for some odd situation, and then what's an Arrhenius, or what is the relaxation? How do you get relaxation time from the correlation function? That's dynamic light scattering, right? So it gets the correlation time, and this is an Arrhenius plot. So this slopes the energy. So you have slow time for one process and fast time for the other. The fast time one has a lower energy because it slopes lower. Then they cross at some point, some temperature. Right, so anyway, so that you don't need to read a paper, like you should already know all that stuff, right? So you can look at the paper, you could give you hints about it. But basically, so this is actually the qualifier question from like 2021 or something, right? So you can do that, I can grade it. Anyway, this one, this guy has there's two papers. One is a paper on making dielectric materials, and the other is a paper on tire compounding. It's also in a book. It's inside a book. So the dielectric one, the dielectric one is a Nature paper from last year. So and it's kind of not a very good paper for this course, for this section, because he doesn't say like what program he used to do any of it. So he does something called so anyway, when you make a dielectric, it stores energy. Like you have two plates, you could have a vacuum, and you could have a capacitor, and you can put something in the middle that makes it store more energy than the vacuum, right? So generally something with a high, where the material can polarize. So you put the field on the stuff and it polarizes, and then that polarization stores the energy of the two plates. So this D is like how much the material polarizes under a field. And then the E, in the end, if you ramp up the voltage, and finally it'll arc across. So that's a breakdown voltage. That's as much as you can get out of the capacitor. So the limiting factors in this is going to be the breakdown voltage, and then the material parameters, like how much does the material polarize, right? And then that will make a better capacitor. So right now, like the state of the art is like barium titanate. Somewhere there's a table of all the materials. Let's see. I should open that up. So all the possible materials to use in this, and they're mostly ceramic, right? So one thing you can say is that a polymer has a much lower breakdown voltage than any ceramic. That's why you have like all the wires are coated with polyethylene, because it's got a low breakdown voltage, and it won't arc across that. So as far as the breakdown voltage, the E, polymers win, like totally win, right? But as far as the polarization, not so much. Like, in other words, you're gonna get in the hundreds with polarization for barium titanate or thousands, and you're gonna get like 2 or 3 for like polydivinyl fluoride, which is a kind of a side group polar polymer that you could use for this application. Anyway, so this is kind of a natural area to use composites, like get the breakdown from the polymer so that you have these little particles separated by something that doesn't break down, and particles that will break down. Yet when you put the field across, there's no conduction pathway, but they can still polarize. So it's a composite material will be like the solution. Also, this is going to be used for short-term energy storage. Short-term can be up to like an hour. So if you want to have something like people are looking at like thermal energy generation, or like your muscles moving can make energy somehow, like a high piezoelectric material or something, then you make the voltage, you got to store it. So then you're going to have a device. If it's going to be on your skin, you're going to make electricity from your muscles moving, and that's going to run your watch, say, or some other biosensor, like a biosensor. Then basically you need to store it in a capacitor so it can run. Like you're always going to be moving somehow. You're always generating electricity. You don't need a battery then. And this thing won't wear out. It's not going to have like so many cycles and it's dead. It's going to be like forever. Actually, you can implant it. Like if it's going to be a pacemaker or something. And it can just generate its own energy from piezoelectric, and it can store it in a capacitor. All right, so it's kind of like a bio. He mentions like bio uses for this or something. So anyway, nonetheless, like anyway, dielectrics is a huge field. Like people just study dielectrics. That's what they do. I mean, especially barium titanate. We had a department head who just did barium titanate his whole career. You know, just that one material. So basically, it's a field in itself. That so nanoparticle part of it. So in other words, it makes it hard to access because there's these world experts walking around. So it's going to be hard to jump into this, you know, to just pick up a paper. Let's see, so somewhere in here, all the materials. There's a list of the materials. 2D dielectrics, this paper, Osada. I might have it. The rise of 2D dielectrics. This is Osada. Yeah. I have that open. So he lists here, he's got a list of all the materials. These are all the 2D materials. And he gives the dielectric constant. So you want to have a high number here to get polarization. And anyway, he in this paper, he finally says that it's like calcium, these calcium oxides are going to be the ones. They're the ones that win the game. You get the highest dielectric. And that so this guy's in conclusion is this, like, so he says like all these materials and then this work, which is the same stuff, that calcium oxide that the other guy said to use. And so the conclusion of this Nature paper is what you would have gotten without using machine learning. So in that sense, and this is the case a lot of times, like you could look at the data and say that's going to be the one. Then they go and use machine learning and find the answer. And then like, oh, they find the answer that you would have said if you just looked at the data to begin with. Right. So this isn't really helping the cause that much. Anyway, what he does, he uses this thing called phase field simulation. Okay, so this is this thing I found. It's from Bohem in Germany, the Ruhr area. So in that area, they have a lot of inorganic guys. Like it's a metallurgy. It's where it's kind of like the metal processing part of Germany. So the schools there are all kind of metallurgy, but this is a pretty good book on this phase field simulation stuff. So it's a category like molecular dynamics, and then the CalFed thing with the equation of state things. So there's different categories of simulation. This is one of them. It's a popular one. You know, so it's usually used to look at phase growth and things like that. So he says like generally a free energy binary system, free energy of one plus free energy of the other, weighted by their compositions. But if you're going to use this phase field thing, you say, well, this is really what it looks like as a gradient, right? So And then in particular, there's this interfacial part that contributes. That's going to have two terms, a surface energy term, and then a derivative of the composition across the gradient. So this, if you ever studied spinodal, which we used to cover in this class, but for some reason I didn't cover it this year. But so basically, spinodal decomposition, Kahn-Hilliard theory, is based on this idea of that interface. That's what drives it, right? So basically, this is Kahn-Hilliard theory, this phase field thing, except put into a simulation. So you have this contribution. So you have a free energy, it changes with position, and then you have this gradient term that's going to contribute to the free energy. So there's a derivative of composition, because in this other, there's no derivative of composition on the parent equation. It's just like that one and that one. There's no interface. So you add in these interfacial terms, and it's in 3D. So everything becomes a tensor, making it complicated, right? So he mentions like Kahn-Hilliard here. This is the only place I found where they mention like all the, finally, this was the one that I'm most familiar with. I think most people, there's this interfacial thing that leads to be able to predict spinodal decomposition, which is in reverse diffusion, right? So anyway, he shows this as like microscopic and macroscopic, and they kind of meet for this simulation business. And this is the kind of term. So he's got this gradient term, that's the interfacial, and he's got a surface energy term. Then this is just the bulk free energy part. So there's three parts to the equation for free energy. Then you're gonna simulate that somehow. That's going to be in the simulation. If you really, I'm not that interested in this right now, but basically this book is absolutely the simplest. This book is great. Like, it's a great book on the subject. It goes through, I'd encourage you to read this book. You can read it in an afternoon. And it goes through every bit about how this works and gives examples and things. So I think it's multiple authors. It's called A Collection of Talks or something, but it's a pretty good book, actually. Anyway, so he uses that. So for our purposes, that's a data generator machine. That's just going to generate what's the breakdown voltage for each of these kind of situations. And he takes this kind of idealized world of particles. So he says, I got particles, I could have fibers. And then if I put a field in that direction, the fibers can go that way or that way. And I could have sheets. So the sheets can go that way or that way. So you'd think, if you're going to make a capacitor with the idea that you want to have no pathway, so you have this low breakdown for the polymer matrix, and then a high polarization for the particles, and it's the multiplying those two together. I mean, I would think that this one would be the one I would choose. Like, in other words, you have plates that block kind of the flow of electrons. Somehow, in my imagination, that would be the best. And the second best would be the fibers normal to the direction of the field. All right, but the phase gradient simulation doesn't show that. It shows that the best way, so a low way is to have the particles. And then the next best way is the fibers going in the direction of the field. And the final best way is when the sheets are going in the direction of the field. So that's because of this concentration of the charge in this, which you can see through this phase, this thing called phase field simulations, right? So he does that, and then he gets this result. Like, the best one is the VNF, whichever that one is here. It's going to be like this one. This is sheets going the wrong way. Or I guess it's VNF is the best one. The fibers pointing that way, and the next best is a V. Is the green one, which is V nano sheets. So the sheets going that way, like D. Right, and so that he gets from single particles, and then you can see he's broken it down into the component parts, and then he does it. Oh, this is showing what in terms of time. So the time dependence of this thing. So the dielectric constant has a frequency dependence, like you oscillate, and it can be used in an AC circuit. So it's important to know the frequency dependence. So he's got like a time series of how this charge develops in the different particles. And it kind of looks like a waterfall, like the So this is just a, let's see, these are just different times for the, I think this is just the field materials. There's 4 mechanisms, cross-sectional electron densities. This is the location of electrons in the material as it goes through different times as it's polarized. And then he finally puts in like a real composite, where he's got like all the particles, and then he finds out, well, this thing makes kind of, you can see what this is, the top one. So these are the same, these are let's see, that K through O is the one's the electric breakdown, the other one's the polarization. Let's see, K through O. Let's see, F, where is this? F to O, parallel nanosheets and volume fraction 1%, corresponding breakdown pathways. P through T, the distribution of local electric field. This is breakdown pathways. This is distribution of electric field. U through W. Where's U? Oh, U through W are these things, just showing the mechanisms of how this works. I guess P through T is the corresponding breakdown pathways. And F through O is the parallel nanosheet volume fraction. Anyway, this is the breakdown pathway. So you can see like the short circuit through this, which is going to limit the whole process. So he shows how that works graphically. Right? So that's the idea of this. And these are from this phase field simulations. And then so he gets that's just get the data. Then he's going to take that. So he has, this is his input number. So he has the morphology, meaning it's going to be 1, 2, 3, 4, which is like spheres. So he's got how many? He's got 5 different morphologies, right? Particles, fibers, sheets. So there's 5 different morphologies, and then he ends up with 2,250 different cases where he changes the morphology, changes the permeativity in a range of 1 to 21, changes the conductivity of the particles, rather of the matrix, changes the volume fraction. And then, so he's got 2,200 examples here. Each of those he runs through a phase field. He gets the breakdown strength, the field strength, the effective permittance, and then the effective conductivity for the system. So he's got 2,221 times 3 parameters is like 10,000 things. And then he's going to score those with a single number, which is like dielectric constant is good if it's high, and the conductivity is bad if it's high. So subtract those two. This is a rate. This is a flow rate. So it has to multiply by some time, which reflects his time, those time graphs that he has here. So he has the 3 different times somewhere. 0.2 second, 0.1, 0.2. So the data actually, with the delta T, it ends up like, if he does 3 times, then it's 30,000 samples. There's a lot of data that's all being generated by this tiny thing. And this is a breakdown voltage squared, because he shows that that's the dependence. And then he shows it somewhere. I think in this here he shows like this whole time. Oh, there's a table of materials. I guess that's his. So barium titanate is like the standard one. Then his calcium, whatever, niobium oxide, 853 blows everyone out of the water. And then it's also got a really high, I guess the best discharge energy density. So summary shows this, the field dependence, but I guess it's here, but anyway, it's shown someplace. So this is his test thing, and he scores his materials according to that, and then he's going to map out and figure out what parameter, what intrinsic parameter led to the best result, the best scoring number using the neural network. And he doesn't show how to do that. He doesn't say what program he used to do that, because he just basically use a shareware program or buy a program to do that. He doesn't say which one he uses. He doesn't say which, for the phase field simulation, say what program he uses for that either. He doesn't give any details about what he did, which is kind of strange. And he doesn't give any references to papers that will give the details. So this paper is just like a showboat, just like look at how good this is. Good thing, and it isn't. I think it's kind of not that useful in that sense. So he's showing the scoring against some of the parameters. Then he comes up with the result, right? So it's in Nature, so you got to read it. That's kind of the point here. This is where he describes the phase field model, blah, 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 that's it. So he doesn't say like, I use this software, this is how you do it. He just gives that one line thing. And then, so I think that's kind of strange, It might be in his other papers, but he doesn't see, he should cite his other paper right there, so you go back and find it. Anyway, I wasn't really going to go hunt for that, but basically he doesn't give the details that you would need to really see to reproduce, which is kind of a necessary feature of a paper. Anyway, so the questions on this, the main question is like, what did he actually achieve by this? Like he shows it's previously known that these calcium things are already there. These are perovskite crystals. So that's a kind of a class on its own of new kind of crystalline material, I guess. It's a really old crystalline material, but it's recently been used for solar energy production using Gretzel cells, because you can make lead perovskites. You can use as a dye basically to collect solar radiation and put it in with something like titania, like a dielectric, and then you can make Gretzel cells with it. Make cheap, like room temperature solar cells. Like silicon solar cells, you have to put through 2000-degree melt of pure silicon and all the separation stuff. And these perovskite lead crystals can be made just by wet chemistry. So it's, and then perovskites are being used for a lot of other things too. One of these is this calcium sheet structures that can be good dielectric materials. So, but that was already known before he did this. So the fact that you're using a high dielectric constant material in a sheet form, so that all this stuff was already known. So the question is like, what did he actually add with machine learning? And he isn't really clear about what that is, I think. So that's kind of the answer to that part. Then he defines all these terms like inversely designed polymer nanocomposite. Means like he's taking the scoring function and he's going back and he's saying like, well, then what would I need to do to make the scoring function higher in the context of this machine learning neural network thing? So I can put in any of those, or he can put in any of his parent parameters. Once he has the weighting functions for his neural network, then he can put in anything he wants in terms of the dielectric constant, morphology. Like he can change, he's got these all down to numbers. So he can put any number here into his neural network and then come out with the breakdown and all these properties. So what's the one that's going to give me the highest energy storage? He can find that out, and then he can say, well, can I make that? And yes, you can make it. And what he finds out is that it's this calcium thing that everyone else is already making. And that gives him much higher properties than that. So yeah, it kind of shows you, yeah, it's like you could use this to design materials. For this particular case, it comes out with a better material than anyone else made. But still, it's not, I mean, so the question is like, is it really true that he's got some value out of this or not? So anyway, so that's A and B, and then C, D, and E are about this tire compounding thing, this Chen paper. So this is perovskite stuff. It's in this thing. Real model and composites, page 281. Oh, that is. Yeah. You just find that. What does this thing say? Frees up memory from inactive tabs. Not now. I say 281, I think. This has some different stuff in it, but one of the things, I think it's 281. This is like the greatest hits of different Polymer simulation people. So it's kind of an interesting book, but there's one chapter in it. They're doing this entire compound. So these people are University of Connecticut has a material science place, and Duke University. She's pretty well known in this simulation stuff, I guess. I don't know him. I guess she's at Duke, yeah, Duke, two places or something. And then I don't know why she's listed twice, but then Northwestern is Materials Place, and then these guys are Goodyear and Akron. They decided not to fund Luxembourg this time. I guess they're somehow involved in this thing. And then so they're interested in compounding tire. Oh, Luxembourg. Okay, there it is. So they have the, so all the money's going through Luxembourg. It's probably coming back to Duke and wherever. But they have to have a Luxembourg guy there. Then the crux of modern science. Anyway, so there's a lot of parameters that go into tires. You know, there's a huge number of components in it. You're gonna have like rubber, but block copolymer, it could be SBR, it could be butadiene, natural rubber, and then different kinds of fillers. There's like 100 kinds of filler you put in, silicate carbon mostly. Also, they can also add calcium carbonate, graphene, all kinds of things. And then what else? Oil is going to make up 40%. There's different kinds of oil. There's alkane and aromatic oil, and then there's heat stabilizers, and there's all kinds of things in it. Right, so you're going to have like hundreds of options, maybe 500 options, close to 1,000 options on how to make a tire, and it's mostly empirical. Like just this one worked, so you're not going to change it. And then the measurement is usually done as this tan delta, like the loss tangent for the modulus, and then you get a peak in it. That's the glass transition kind of. So basically you can do that at different frequencies, and you can get information, all the properties of tire have been mapped out to that. Whether that works or not is another question, but that's the approach they're using, is to kind of say they can use that. So they get, you know, you're just going to get a bunch of numbers. So you have a number, you have the input numbers. It's the same thing as last paper. Like the input numbers up here, you have like 1,000 different things you could change. And then on the other side, you have the property, and basically like one property we're looking at, it's this dynamic mechanical curve. And they got to try to predict the dynamic mechanical curve. So they're going to have a learning process. Take the 1,000 parameters, and then say, like, I can break those down into neural networks and have weighting functions, go through all of them, finally get to 1 or 2 parameters, and then go to this other thing, and how do they correlate with each other, and then get the weighting numbers to match up. And then I have my neural network set up. Then go back and say, what do I want to have done with this tan delta curve? How do I want that to look, which isn't known. Okay, so basically, you said, I know what I want the tan delta curve to look like. Then you go back and say, run the weighting functions backwards and say what my formulation would be. And then that would be the magic tire that you can make for whatever condition you want it. It depends on if it's a race car tire, a truck tire, or a car tire, and if it's being used in the north or the south. That's cold and warm. And basically every car has a different rubber that would be perfect for it, because it has a lot to do with the weight of the car and like how it corners or whatever. You know, so everything, there's going to be a perfect rubber in tire for every car, and it's not going to be the same for all the different cars. So you could use this over and over again once you get the neural network set up. So you can see why Goodyear might be interested in it. I'm sure that Michelin has already done this like 10 years ago, because Goodyear's always behind the curve on this kind of research. But basically, probably because they're putting all their money into Luxembourg, you know, France would have been a better bet. So, but France is, you know, Michelin actually had, like France has like a CIA, and they work with the French companies to spy on US companies, at least in the past. Like nowadays it isn't worth anything because US companies don't really do much, but basically they're probably going to somewhere. Basically their government and the companies like work together that way. So they actually have spies that go around and like steal corporate secrets, like bring them back to Michelin. Yes. In addition, Michelin puts a ton of money into research. So it's hard to tell. It's hard to tell if the spying thing actually bore fruit, because it probably led them down the wrong road, because they probably already knew how to make a better tire. You know, so anyway, the Japanese Bridgestone's doing pretty good now in terms of research. Koreans kind of coming up, I guess. Germany's always had a decent effort going. Continental, but they never seem to get the product out the door that Michelin does. So Michelin's the best tire company, like by far. They make the best tires. Everyone knows that. Yeah, and Goodyear was a contender early on, and now they fell out of favor. You know, they have Goodyear has good polymer chemists that make like polymers that are magical, you know, for different conditions. Anyway, so this is the kind of thing. They have this model. See, this is a Maxwell model. Each of these separate Prony series is a Maxwell model from what we already had. So there's a question like, so this thing has a time constant associated with it, spring in the dashpot. It's going to be like the modulus over the viscosity to give it a time constant. So this is just a sum of time relaxation curves, like just like in the other paper or the last paper we have some number and it's exponential decay. So exponential minus t over tau is going to fit that curve, and that's the response you're going to get from this each of these things. So they have 27 of those to model it, and then this thing. So and from that model they can reproduce a tan delta curve. Now, this doesn't necessarily have to have any meaning, but that's what they did. You know, so they have this model. They get these 27 taus, and then in addition to that, they put in just a static, non-thermal, non-time dependent spring on this thing, which I guess it seems like that would just add the spring constant to these springs, but I'm not sure how that works. Anyway, so that's what they're doing. It's kind of interesting to look at. They get a correlation function. So this is the same to get. All right, so they want to relate this back to the structure too. Like it's in addition to the dynamic mechanical, they have the structures. They take the structure. This is kind of interesting. So they take the structure in SEM image, which is a kind of a micron size scale, 1 to 10 micron. And so it's kind of moderate resolution SEM. Then they binarize it. So make it into ones and zeros. And then they use a correlation function. So they take a correlation of all the intensities at all the positions and multiply by each other, you get a correlation function in terms of distance. And then from that correlation function, they claim they can reconstruct what the structure was. So so in that sense, they can make as many structures as they want that have the same correlation function they say are the same as the original material. And then they use that in a finite element calculation of mechanical properties. I would say finite element means you're going to make a grid out of this, find the modulus at each point, and the stress between the boxes, and then just construct a mechanical model, like a composite model for the whole thing. So this software is a finite element analysis. It's generally intended for like macroscopic, like a page. Right? So you can bring it down to maybe 10-100 micron, which is good for SEM. And the dynamic mechanical is really talking about the nanoscale response. It actually, the spectrum goes from kind of atomic all the way to macroscopic from that mechanical testing. If you figure out what size scales are impacting the different parts of it. So anyway, this is kind of interesting what they did here. It's kind of like weird, but it's interesting, I think. And then anyway, so this is just showing how a correlation function works. Oh no, this is the neural network, I guess. No, this is a correlation function. And then the finite element is just a software you buy, it'll spit out the modulus from that thing. And then so they do basically match these things up and predict how the predict the dynamic mechanical curve from the thing. And then come up with like a best formulation for a tire in the end. So it's kind of long actually, but basically I just wanted you to glance at this and see like people are doing this too. This is, I think, last year also. It's a question in this thing. During mowing, blah, 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 discuss, da, 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 can explain how each of the Prony series, this is just like what is a Maxwell element. No, it's how you get a time constant out of that. Then This is another paper. And realize basically we can try to make sure this class of polymer management products. Account for microspectral. Describe things method. So things method, this is the method they use to do the micrograph thing. I have that open. Things method. Thing. So this is just, oh, this is Breeson also from Duke, right? And then some other people. So just, and what's journal is this? Composite Science and Technology. So it's kind of a decent journal. Just showing, that's exactly the same thing in the other paper. So they just lifted this. This is kind of more, maybe more detailed. So you can see they're generating images. It's kind of interesting. I mean, this alone is kind of interesting. Like everyone's going to be doing some SEM at some point, and like, what can you do with it? This is an example of maybe what you could do with it. Maybe it's not suggested to do that, but anyway. And then Zoo killers in terms of loading, percent geometry, blah 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 blah. Describe the behavior. For instance, how is tear resistance? This is just critique this thing. So he's got these parameters so that when you add carbon black to rubber, the main thing that happens is the tear resistance goes through the loop, right? So in other words, if you take rubber with no carbon black in it, it's like an eraser, it just falls apart. The pieces come off. If you stretch it, or if you abrade it, it just falls apart. So adding the carbon black, the main thing that it does, there's two main things: conductivity, you can't build up a static charge in it. And the other is that like this tear resistance goes through the loop. Just add in, well, they add a lot of carbon black, like 30–40%, right? Basically, that makes it so tough. You couldn't have a tire without the carbon black because it would just wear down the minute you went to the road, right? So that's absolutely the main thing that you're putting it in for. The other things are all fluff, like consume, dynamic, mechanical. They don't mention anything about the tear resistance or any of these features. Mullen's effect is like when you take a balloon and stretch it, and then you blow it up, and it's easier to blow up after you stretch it. So you break up the carbon black network. They don't talk about network because you're only looking at one size scale, just the SEM size scale. So they don't talk, the network is like macroscopic, right? So they don't mention that. And the pain effects related to the Mullen's effect. It's got to do with the strain amplitude dependence. Usually you're doing like less than 1% oscillatory strain, but you can bring that up to like 10%, and you find out that the network breaks down there too, right? Frequency dependent thing. So since they're not looking at anything bigger than these 1 micron particles from an SEM, then they can't see any of these things or any of the interfacial properties or anything. So you could critique this paper that way. That's the point. Anyways, there's a lot in that thing. There's like 3 or 4 papers and chapters and all kinds of stuff in that. But basically, you can look through it. Then I wanted to just mention this other paper. This guy. Let's see what I got here. I think I already opened this, but maybe not. Large TG shift. This is the case where you have, so you're gonna, if you add clay, people have talked about, so you take clay, like you dig it up in the dirt, and you can put it into different acids, and you can break apart the layers of the clay, right? And then you can make nano filler particles. You can make a nano composite. It's called exfoliation. Foliation is like foliage, like leaves. So you're breaking the leaves apart. So exfoliation means you're taking leaves off of something. So and you can do that chemically with clay. And then you can make it, you can also drive like polymers between the channels in the clay, the galleys, they call it, the galleys of the clay. So like you have the clay layers, and there's these galleys that have ions on them. So you can either neutralize the ions or ionize the polymer, and it can force into the galleys and separate them. So you can exfoliate with the polymer, or you can do it with a chemical, right? And then mix it after. This idea of simulating these like things where you have like layers, ionic layers, and polymers in between. So this is a bilayer, and a monolayer would be just one polymer layer in between. And then they're doing that. So they're looking at that kind of material with X-ray photon correlation spectroscopy. So they can do an X-ray pattern on this, then you can get the stacking period at kind of high Qs, like 0.1, maybe 0.4, there'll be a peak associated with those stacking. So it's not a diffraction peak exactly because it's water disorder. And as you exfoliate it, that peak gets to larger sizes, so it moves to lower Q, and it also disappears at some point. So it's a sharper peak, and it becomes less sharp as you exfoliate. So you can watch the exfoliation process with X-rays. Also, if you take time, so if you have a collimated X-ray, like at a synchrotron, that's really bright and monochromatic, then you can get a speckled pattern from it, just like you get from a laser. Right? And you can look at the speckled particles, dots move around. Basically, that's got to do with the dynamics of these layers, of how they're shaking. And you can do that as a function of Q, or you can do it as a function of time. If you do it as a function of time, you get an exponential decay, so you get relaxation time from that. Exponential minus T over tau gives you, it's just that decay, and you just get a tau. So he does that, he gets tau as a function of 1 over T, he finds out it's linear. From that, he gets the activation energy for these things doing that as a function of looking at either a bilayer or a monolayer of the things. So anyway, so there's some stuff in this. This is the second paper, so it's a second subject, but this is much simpler than the other things, I think, in the sense that you should already know all this stuff. Most of the stuff you should know. A little bit of it's like taken from dynamic light scattering. It talks about X-rays, which is something newer. I mean, dynamic light scattering is from the 1980s, 90s. And this XPCS is like 2010, maybe to now, so the similar thing. I mean, he even shows, I think, in here these are the peaks from the clay stacking, I guess. And then he does a DSC, and he finds out that when it's a monolayer, he gets a single glass transition that's similar to bulk. Like one of these is bulk. I think this is bulk. This is bulk for what are the different things? Different speeds. So with a DSC, you put your stuff in a chamber and you're going to heat it at a certain rate. So the faster the rate, the bigger the signal you get, because your signal is like heat per time. So the faster rate, you should get a bigger signal. And the slower rate, you should get something more at equilibrium. Smaller signal, but should be more equilibrium. So he goes through these different rates. Also, this would say something about the rate dependence of what's going on. So he's measured a tau with X-ray, and the tau is like in the seconds, like 10 seconds, 100 seconds. And this rate is like degrees per second. So 5K per minute, I guess. So these are on the same order as the time constants that he's getting from the other thing. So something kind of interesting that the rates here are similar to the rates, time constants he's got. And then when it's just pure polymer, there's no rate dependence. When he puts in the clay, there's a rate dependence to the glass transition. And also when he has a bilayer, and he has this bilayer structure, he's got two polymers within it. Then he gets two TGs, and he says one of them is a bulk TG and one's the other one. So he's saying there's a TG here, and there's a TG there, so it's two TGs. So this TG's at 445. So these TGs are all at higher temperature. That means that they're stiffer. So it kind of makes sense that it would be at a higher temperature because it would be stiffer because it's confined. So when the polymer is stuck in there, it's not as easy for it to wiggle. The TG is kind of where it starts wiggling. At 9 millunits start to wiggle. So when you confine it, the 9 millunits are kind of stuck. They can't wiggle. It takes more energy, more temperature to get the wiggle. So the TGs are at a higher temperature, right? And then that's some of them within the bilayer are able to wiggle like a bulk, and some within none of them in the monolayer are. That's kind of the theme of this paper, in a sense. So that's where he's coming from. This is a picture of his speckle pattern for X-rays, which people probably find hard to believe, but he has a picture of it, so it works. And you do that at different times, and you can get a correlation function for the speckles, and that gives rise to a correlation function in time. So you do it at short times and at long times, and the correlation function changes. And at long times, the system relaxes, so there's no correlation. So it goes to 0, and at short times it goes to 1 because there's perfect correlation at 0 time. So then in between you have this decay function, it's e to the minus t over tau. Then you can get the relaxation time from that, which is here. Steep one has a higher energy of activation than the shallow one, which is the bilayer, which doesn't make that much sense. And also the bilayer is a slower relaxation than the monolayer, which doesn't make that much sense either. But basically, that's what he found, so you can't really argue with that. And then, I mean, he gives an argument for why that's the case. It's an interesting paper, I think in general. It's got a few subjects that are abused that you could talk about. There's some questions just about that in here. DSC traces, bilayer, explain the two regimes. That's like bilayer has some bulk in it, and the monolayer doesn't. This says how big the galleys. So the galleys are 1 nanometer, and the polymers, if you stretch the polymers out straight, they'd be 100 nanometers, and the RG is 10 nanometers. So definitely the polymers are deformed when they fit into these galleys. That's kind of the point of this. So when the lateral dimensions like 300 nanometers. So polymers don't dangle out of the galleys. Oh, it's raining out now. Pretty hard. So hey, I think the dimensions, it's really important to look at the actual sizes of things instead of a cartoon. Like, in other words, people can say things and then show a cartoon, but not until you start doing the size things. Like you have to actually put little rulers down and say, is this possible? So this says, yeah, that seems to be pretty possible. Right. So the point of this is just to say it's reasonable what he's saying. It could happen. I mean, he's not looking at the other dimension, like the chains are stuck in this hole. True. And the dimensions, if you look at it in the 2D plot, that makes sense. But there's another dimension that they could be squiggling around in that way. So that isn't really considered here. He just shows a slice of this sample. He doesn't show that if you did a profile of it, the thing's actually worming around with these sizes, right? So there's a little bit of a lie there, but XBCS, explain what G2 is a correlation function. If you look up the dynamic light scattering, you can figure that out. And then this Arrhenius plot gives you the energy, activation energy. That means that this has to be thermally activated, which glass transition is thermally activated. And this is his T over tau thing. So this gamma is 1 over tau. Right, and it's Q dependent because it's at different size scales, it's relaxing in different ways, and that Q dependence should be like a diffusion dependence. So it should go with size squared goes with this time. Right? In other words, the root mean squared of the displacement is diffusion coefficient times time. So the square root of time. So the time would go with the square root of distance, but whatever. So he didn't show that plot, I think, but and it may in the supplementary. But for the tau plot, activation energy. So the monolayer has a lower activation energy than the bilayer. And that might have to do with this other direction, like because it's only looking at the slice. It doesn't make that much sense. The slice and monolayer is like confined more than the bilayer. It should have a higher energy of activation or lower. But maybe if you looked in the other direction, or the bilayer could entwine or something in the other direction. So you could have a kind of entanglements. I mean, who knows? He never looks in the other directions. That could have something to do with that, but, or it could be something else. Anyway, it's mostly just intended to introduce some things and get you to talk about it, like to say something about it. So that's generally the way the qualifier questions are supposed to be. Like here's something kind of interesting. What can you say about it? Like here. Like, what is it? What is this plot? Like, what does this mean? And things like that. So there isn't really a right and wrong answer to it. It's going to be just whatever you can say, everyone will say something different. And it's going to come from your background, like whatever you know. So basically say anything that makes sense. That's good. You say stuff is just gibberish, that's not good. Like gibberish will actually be a negative thing, So it's better to say nothing you say something, but you say little. Don't just start blowing off like Chat GPT and something that they know about. But the stuff you know about, make sure you put down. Like I know, or even relate it back to classes or something, or some other thing, even if it's unrelated, it could help. But basically it won't help much. It's nice if you could say something coherent about this thing. Like if you heard a talk by this guy, then what question would you ask him? Like the other dimension, that would be an obvious question to ask. Like what about that? And why is the energy different? Why is the energy different in that way? And things like that. So anyway, if you want to do that, you can do it. And I'll count it in as another quiz grade into their homework grade into the thing. If you don't do it, I'll just add in the last one. But I think everyone, there's two guys that are going to get a B no matter what they do. I think I figured that out. And then everyone else has an A. And I emailed them so they know that. So they don't need to do this homework. Because even if they don't do it, they still have a B. If they do it and they got like 100, they would still have a B. So there's no point to do it unless they want to. And then everyone else, like the guys from chemical don't need to do the second problem. You might want to calculate what your grades are if this thing actually impacts it. It might not, like if you're above 90, then you get an A. It's not going to get any better. I haven't calculated it for everybody. So I only did it for those two guys because I didn't want them to waste time doing it if they didn't want to. So anyway, so whatever you want to do is fine. I'm gonna be traveling, so I'm not sure when I'm gonna grade these. I might get them graded pretty fast. It depends how many you guys turn in. But I think I can just give you guys grades without this.
When's the due date?
The due date's Thursday next week. Yeah, because that's the last day of exams. And I think they give us like two days to grade it or something. So if I can't grade it, I gotta be in like Germany. So if I can't grade it by Friday, basically I'll just kind of figure out how you grade it. I think basically everyone got an A except for two people. So it'd be good if you looked at this thing, but so I think it's better to try to do these alone too, so that you get a feel for like what, because everything else has been in a group. So it'd be good to kind of get a feel for how you individually do. But anyway, so I think it should be okay. So thanks for coming, guys. The 4 guys that showed up every class, 2 were missing. One's an undergrad. So.
Yeah, okay.
But anyway, appreciate that you showed up. Guys online, thanks for
Thank you, Prof.
Let's see. So yeah, I think we got a mixture of people, different expertise and stuff. It's good. So hopefully got it geared a little bit towards what you're interested in, I don't know. So anyway, so hopefully it's okay. There's an infinite amount of stuff you can cover. So.